Okay, so I'll now start lecture 10, which is the fifth in the series of neutron diffusion. This is part of a course NE402 Intermediate Nuclear Engineering on diffusion and transport of radiation and Monte Carlo simulation. The course content is shown over here. As I said before, this is my name, my telephone number, personal website, official website, and personal website. So please do go through these lectures. This is especially for advanced undergraduate students and graduate students of nuclear engineering, uh, mechanical engineering, any engineering program, elective, and of course, mathematics, physics, and researchers. There's also applications at the end for health physics. Okay, so in the last lecture, I was discussing two group equations for a sphere, and I went through very elaborate derivations of the two fluxes, phi 1 and phi 2. And I showed you a computer example for a slab with these two equations. If you see lecture 9, that I had started this and took these four boundary conditions. This is phi 2, so we've got Dirichlet boundary conditions, and we've got a Neumann boundary conditions. This is the two-group data for water, and there's a left incident neutron source of strength 1. The exact solutions are given here in terms of the exponentials for unknown coefficients, which we find through the boundary conditions. The age, neutron age tau, the diffusion length L, and the value of the coupling uh, with phi 1, phi 2 and phi 1 coupling. So as I said, this is the MATLAB program that solves this equation. The density of water is taken to be 1. Molecular weight is 18, Avogadro number. You find the number density of water molecules, the removal microscopic cross-section, removal transport cross-section, the diffusion coefficient, the source strength, the microscopic cross-sections, L square, and tau. Beta, the slab thickness in the x direction is 20 centimeters. This is after you've applied the four boundary conditions, you get a matrix. You solve the coefficients A, which come out to be A1, A2, A3, and A4. So that completes this solution A1, A2, A3, and A4. Once you've got the coefficients, you can plot the fluxes, which I've done here with the functions in MATLAB. And the idea was to show you the shape of the fluxes. Now, in this particular case, the fast source is incident from the left side. So you see that there's a gradual decay in the fast flux, in the population of the fast neutrons, which build up the thermal flux. It goes up to a maximum and then decreases itself. Now, why does this come down? As I mentioned last time, because there's a leakage and because there's a removal into the lower energy group, group 2. Why does this come down? Because there's a leakage of thermal neutrons and there's a removal of thermal neutrons. Why does it build up? Because there's no thermal flux at the left boundary, so it takes time for the fast neutrons to slow down to these neutrons. So gradually, a population builds up, reaches a peak, and then begins to die out. The shape of the fluxes is very telling. It's very illustrative of what is happening. And whenever you find fluxes, then you should also, after doing the mathematics, you should discuss physically what they represent. There's a lot of data in Lamarche and Barata, and I'm showing you some over here for the thermal data at 20 Celsius for diffusion theory, neutron flux in an infinite medium. Now you can see for water, which is the primary coolant and moderator used in over 440 nuclear reactors in the world. Heavy water is used in the Canadian deuterium uranium reactors. Beryllium is used as a reflector, and in the form of an oxide it becomes stronger. So beryllium is a very useful material in nuclear engineering. Graphite, which is carbon, is also very important. The world's first nuclear reactor, made in the University of Chicago by Enrico Fermi and his team, used graphite. It's called the graphite pile also. So for water, you can see the density of all these four and the diffusion length to thermal, the thermal diffusion length. So it's about 2.85 centimeters for water, 100 centimeters for heavy water. See what a big difference it makes from going from light water to heavy water. So why do you use heavy water? Well, in heavy water reactors, you don't need enriched uranium. So that's the advantage. Beryllium has 21 centimeters and graphite 59 centimeters. Now, these numbers are all very useful from the design of nuclear systems point of view. Now, so that was what I was talking to you about non-multiplying systems. Now let's come to multiplying systems. Multiplying systems are, of course, the main systems, the main field in nuclear engineering, because they involve uranium and plutonium. So all nuclear reactors, critical assemblies, subcritical assemblies, nuclear weapons, uh, whatever you can think of in nuclear engineering involves multiplying systems. Of course, you do not have multiplying systems in hospitals because you don't like to use uranium and plutonium near human beings. But there you've got radioisotopes. So of course, those are not multiplying systems. So let's write down the two-group diffusion equations for a bare core. Now, what does the word bare core mean? The word bare core, I'm going to just show you Godiva. Just take a bare sphere, for example, of U235, don't surround it with anything, and see how much of it you need to make it critical. So these are the two group reactions, so the two group equations for, a bare core. The subscript C represents core, because a few minutes from now I'm going to surround this by a reflector. But right now, let's say you've just got a core. So this is the leakage term, this is the capture term, the removal term, sigma R1. And this is something new you're seeing now, because there is fission taking place in the thermal group. So the number of fissions depends on sigma 2 multiplied by phi 2. Phi 2 is the thermal flux. This is the relevant fission cross section. And of course, if there's fuel and moderator, if there's a mixture, then you're only interested in the fuel part. So you have to calculate the number of fissions in the fuel. After that, you multiply by K infinity, divide by PC, and you get the source term. Notice there's no independent source here. This is the fission source coming from down here. So the two indirect, you can call them sources in the group 1 and group 2 equations. The group 1 source, it comes from fission in group 2. The group 2 source comes from the slowing down of fast neutrons, which are contributing to the lower energies. So it's a sigma 1 removal from phi 1 in the core. We multiply by the resonance escape probability P in the core, because remember those very high peaks in the central region which represented resonances. So these are those neutrons which have come down from here and have escaped the resonance escape. They have escaped the resonance peaks, resonance absorption, and they find themselves in group 2. So in group 2, we've got leakage, we've got removal, and we've got a source term. Now, again, the boundary conditions, let's say you've got over here, you've got nothing coming in from a direct source. So I'll put both those to 0, and at the extrapolated boundary, which is R bar, which is the physical boundary plus the extrapolation distance, both the fluxes vanish. Now, again, if you assume a uniform material, i.e. no space dependence in the material properties, then D and sigma are constant, and you see what a convenient expression we get. Now, notice there's still one coefficient left over here. And how do you get that coefficient? Well, that coefficient comes by the reactor power, the thermal power coming out of here. So you can have a critical assembly at any power, so to speak. In principle, you can make it critical at a low power, you can make it critical at a high power. So depending on how much power you want to produce out of this, you uh, essentially multiply this and you can find out the value of A from here. So if you look at this, there's a sine term, there's a sine hyperbolic term, and it's so easy over here. Of course, sine R over R, no problem. Uh, you can use L'Hopital's rule. So the derivative of this becomes a cosine. The derivative of this becomes a 1. So finite divided by finite is finite. And over here, because cosine of 0 is 1, so this becomes finite, and the derivative becomes 1. So this is okay. Now this uh, is multiplied by a very small number, and I told you last time that this diverges. So there's a little bit of divergence here at r equal to 0 multiplied by a very small number. Now let's come to two-group criticality. Now two-group criticality, that means to design a system that is critical, which can self-sustain a nuclear fission reaction based on two groups. So the one group theory was not very useful. So either you can use a modified one group theory or a two group theory for criticality calculations. So let's come to practical things. A more accurate theory incorporating fast non-leakage probability is based on Fermi's slowing down equation, which I think I did in lecture 6, where the neutron age had units of centimeters square, and remember what it was physically. So this gives the one group critical equation if you use the one group. So in the one group, the K effective has got to be 1. Remember that cycle where you start with a source and epsilon p eta f times the two non-leakage probabilities. Now this is the non-leakage probability for fast neutrons, and this is the non-leakage probability for uh, thermal neutrons, 1 over 1 plus b squared L squared. So how do you solve this equation? Let's say that you want to find b squared. It's up here and down here. So let me say that b squared tau I call x, something I'd like to find. So if you look at this part of the equation, so k infinity e to the minus x, and the denominator I'm going to write as b squared is x over tau. So x over tau, and here's the L squared. So this is a transcendental equation. So I can solve this by plotting this side and this side separately and seeing where they intersect. So wherever they intersect, you can find B, and B for a sphere is pi over r. So you can get r, the critical radius, from pi over B. And so that equation, if you go back to chapter 1, lecture 1, so 1, 2, 3 were on the introductory concepts on which I took you through the K effective and K infinity. So if PF is the leakage probability, then 1 minus PF is the non-leakage or survival probability. So this is the survival probability of fast neutrons. This is the survival probability of slow or thermal neutrons. So if I multiply it by the K infinity, the multiplication of the infinite system, so I should get the multiplication of the finite system, and that's what I'm interested in. So p to the f I can also write as an exponential, and if this is a large number, so let me just write it as, so 1 minus b squared tau, 1 minus b squared tau is 1 plus b squared tau to the power minus 1, so I can bring this down in the denominator. The higher terms are, of course, uh, are much smaller, so they become, this is okay, it's acceptable, it's got a small error. So it holds for large reactors for which b squared tau is much less than 1. Similarly, the thermal leakage you can write like this. The non-leakage is 1 minus this. And so you can combine the L square and tau, and you can write what is called a modified one-group critical equation. I'm just going to show you how this modified one-group critical equation is used practically for calculations of critical systems. Before I take you to practical aspects, let's brush up a little bit more on our theoretical base. So let's look at the adjoint diffusion equation. Now I told you adjoint has a mathematical significance and it has a physical significance. So let's look at the mathematical significance first. So for the one group diffusion equation, which is a second order ODE, the operator L is self-adjoint. So you can show that there's a property of self-adjointness that, for example, the second derivative, d2 dx squared, is self-adjoint because of its being second order. First order is not self-adjoint, as I'll just show you later on. So in contrast, the two group equations with, now I'm saying that fission takes place in both groups and they appear in the fast group and they do not appear in the thermal group. So then this becomes the two equations, which I can write in matrix form like this, putting these two over here. Now what you see over here is a div times a grad. So in matrix form, can I write it as M 2 by 2 matrix with these operators? Multiplying on a vector phi, which is the fast and the thermal flux. Now, adjoint operator. Adjoint operator says that we write it as M plus. So the forward operator, or you don't have to call it the forward operator, it's understood when you don't say anything, it's understood that it is the forward operator. So when I talk of operator, I mean a forward operator. When I talk of a adjoint operator, then you have to specifically say it's the adjoint operator and it's the backward or adjoint equation. Now, adjoint equation has a connection with the Lagrange multiplier, which I'll come to when we discuss optimality and optimization. So the adjoint operator is obtained by getting the transpose of M. So if you look over here, so the transpose of M means that this thing goes down and this thing comes up. So for a 2 by 2 matrix, it leaves the diagonal terms this way the same, but it changes this. So it essentially changes mathematically the equation. And this is what the adjoint equations look like. Now you can solve for phi 1 plus and phi 2 plus. You can apply boundary conditions. And I'll show you all that when we come to transversality conditions. So there's a whole theory of the adjoint equations. They are very useful in nuclear engineering because as my own PhD supervisor, the late Jeffrey Lewins at Cambridge University wrote in a book. He has a book on the importance function. And there's also the physical use of the importance function. It tells you how important a neutron at a certain point in phase space is to the response of interest. So if you're trying to measure something which depends on thermal flux, then of course a fast neutron is not important. The thermal neutron is more important. So that tells you, and it's used a lot in areas such as shielding, that which neutrons are important, so don't waste your time on those that are not important. So the forward and the backward fluxes are very useful in nuclear engineering for design. Now let's come to two-group diffusion in a reflected system. In a reflected system, essentially the purpose of reflecting a fissile core is to make it smaller, because the leakage that takes place from the boundaries, the leakage of neutrons, you want to reflect them back into the core so you don't lose them. Now, certain materials are good reflectors and certain are not. Those which absorb, for example, beryllium is a very good reflector. Now, beryllium, if you surround beryllium around a uranium core, then the neutrons come back. If you surround it with a heavy absorber, like iron, so you won't get so many neutrons reflected back. And of course, iron is much heavier. The density of beryllium is much less than that of iron. So let's look at reflected systems. So nuclear reactors are reflected, and because you don't want to make them huge, you want to reduce the size. So for better neutron economy, we study core reflector systems. So let's apply the two-group neutron diffusion equations which we have just studied. And so now I'm going to write the two equations which I just considered with you for core and for reflector. Now, reflector does not have a fissile material, so there's no fission going to be taking place in a reflector. And you don't want to place a source in a reflector. So a reflector is exactly these equations with, of course, different properties without the fission. So the structure of the equations is the same, just that now we've got 4 equations. So the size of the problem is going to become bigger. Conceptually, the problem is the same, that now you've got 4 variables. So the vector phi consists of phi1, phi2 for the core and phi1, phi2 for the reflector. So these are 4 equations. So for 4 equations, a nice, neat way is to get a 4th order ODE for, and you can show a 4th order if you rearrange these. For example, you take, let's get rid of phi 2c. So phi 2c from here, if I put this on the right-hand side, so this becomes, in terms of phi 1c, it becomes equation 354. Now 354 has mu square and lambda square, which look like this. See how similar they are. They've got the neutron age, they've got the diffusion length, they've got the K infinity, and there's just a difference of the sign over here. So when you write a MATLAB program, be careful because this can be a very small number. So this, of course, is okay because they're both positive signs over here. Okay, so let's solve a 4th order equation. So that should not be difficult. And so I'm now going to follow Lamarche and take a uniformly distributed fuel. This is in standard textbooks in nuclear engineering, so it's in my textbook also, that if we start by looking at a uniformly distributed fuel, the coefficients in the above equations are constant, and you can obtain phi 1c, phi 2c, phi 1r, phi 2r. It becomes simpler if you assume them to be in terms of functions x and y. Now, it's also a mathematical part of the structure of these equations that if you look for a solution of phi 1c in these in the form of ax plus cy, then it turns out that phi 2c is also ax plus cy, but with coupling coefficients s1 multiplying a and s2 multiplying c. Now, similarly for the reflector, you look for functions z1 and z2. So phi 1r satisfies fz1, phi 2r again is related to this by a coupling coefficient s3 and g. Now, when you put in all these assumptions up there in those 4 equations, then you get coupling coefficients s1, s2, and s3. And the functions are x and y. For a slab, they're just cosine and cosine hyperbolic functions. For an infinite cylinder, they are the Bessel functions J0 and I0. For a sphere, it's sine over r and sine hyperbolic over r. And for the reflector functions, you can see for an infinite slab. Now, reflector doesn't begin from 0, it begins from the end of the core. So that's why you'll see that the x coordinate begins from half the core width plus b. B is the width of the reflector, minus, now you start counting x from there, and mod because you take symmetry on both sides. So this is for a finite reflector, this is for an infinite reflector. So finite cylinder, finite sphere, infinite sphere. Now let's look at the 4 boundary conditions. The 4 boundary conditions are that you've got flux continuity between the core and the reflector at the interface. So there are 2 boundary conditions over here. You've got current continuity at the interface, so Fick's law, D1, so for if you really want, you can put a minus sign here and a minus sign here, because Fick's law is minus D grad phi. So the minus minus cancel out, so you get continuity of D1 phi prime at the core and at the reflector. So 364, 65, 66, and 67 are four boundary conditions, interface conditions. When you put them together, then you get, because these are homogeneous equations, so you get four linear homogeneous equations. Now, if you if you try to solve them, you just get four zeros. So that's no good. So the only non-trivial solution of these four by four matrix is obtained by requiring, by Kramers' rule, which we all study in Calculus 1, that the only non-trivial, in other words, the only physically sensible solution that you get out of this is when the determinant of those four boundary conditions, when the determinant, I put two big straight lines on the left and right, meaning the determinant, when the determinant of this is zero. Now I'm just going to show you how we solve for the determinant of this to be zero. Look at 368. These are functions x, y, z1, and z2. X prime, y prime, z1 prime are derivatives of cosine or sine or cosine hyperbolic or sine hyperbolic. So, and they're evaluated at the interface. So either you know the size of your system and you find the composition, or you are given the composition and you find the size at which this determinant becomes zero. So this determinant is useful. So when the material properties are given, the critical dimension can be determined when the determinant is zero. Conversely, when the dimensions are given, I say dimensions because for a cylinder you'll have R and H, but for a sphere you'll only have the radius R. So when the dimensions are given, then the material properties such as enrichment, because that's what you really want to find in nuclear engineering, that what is the enrichment that's going to make it critical. So you can determine either the criticality given the material properties, given the size, or you can determine the size with an enrichment that you've got. Okay, so let's, for example, just for application of this, let's go through a uranium water dilute homogeneous solution, which means that you've got a glass or a pot in which you have lots of water, and you take a spoon, just like you put spoons of sugar in your tea or coffee. So you take spoons and start putting U235 in there. Now you've got very little sugar in your tea, right? So you call it a dilute homogeneous. Homogeneous means that the sugar has dissolved in the tea or coffee and it tastes good, but you cannot see the sugar. So just like that, assume that U235 in a spoon, a powder U235 you take from wherever you've got it and you put it in a pan of water and you mix it. And you mix it to a ratio of 1 to 500. And now let's apply, so just a tiny bit. So the ratio is 1 U235 to 500. So that's why the word dilute is being used. So it's a dilute homogeneous solution. Can it go critical? Yes or no? So, well, think about it. And so these were the experiments done in the initial days of nuclear engineering at Los Alamos. And so can it go critical? And let's see if it can. So let's apply the two group data. Now, I'm going to give you a little talk later. How do you get data? That's a separate thing. But here, let's say we are given for group 1, which is a fast group, you're given the diffusion coefficient and the removal coefficient in the core. You're given the diffusion coefficient and the removal macroscopic cross section in group 2 in the core, and you're given the water microscopic cross section in group 2. You're given the absorption cross section in U235 in group 2. Water does not have, of course, any fission or very much to contribute to the absorption. So we say mainly in the dilute it's uranium. Now, when you do that, then the previous solutions I showed you were for core, and you get for reflector. So see them carefully, and I think we've gone through the structure of those equations. and this is what the fluxes look like. Now this is in a sphere, in a spherical reactor, which is critical. So the core extends from the center to about 22 centimeters. So with your hands, just, move your hands left and right till you make a sphere of about uh, 22 centimeters. Now 22 centimeter radius is about 44 centimeter diameter. So just do it with your two hands so that you get an idea that how big it is. You know what a meter is. So a meter is slightly more than 3 feet. So this is going to be 22 times 2, which is 44. So roughly just say what half a meter looks like. So 1.5 feet. So that's going to be the size of the ball of the U235 and water uh, mixture. So about 22 centimeters makes it critical. If you surround it with a spherical shell that extends from 22 centimeters to about 40 centimeters. So now 40 and 40 is 80. So let's say now move your hands left and right to about 1 meter, and that's the size of a U235 water dilute mixture that gets critical. So look at the flux. The fast flux comes down. Now, I've normalized it over here so that the value 1 should be that of thermal flux. Why have I kept the thermal flux 1? Because that's the power that's going to be produced. So I'm not interested in fast flux. I'm interested in thermal flux because the power, the heat of the reactor comes from here. So the fast flux dies out. That's, remember, fission took place here, but those neutrons went in that group. So now they die out over here. They die out over here. They don't leak because they're too strong. They're too energetic. They go right through the reflector and they go straight. Nothing stops them. Nothing sends them back. But if you look at the thermal flux is of course less than the fast flux because these neutrons are born out of these neutrons, which slow down. So they slow down, 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 and it's a symmetry. So there's on that, so symmetry, it's a sphere. So you can see the current here is 0 because the gradient is 0, and here also the gradient is 0. Can you see it's like a straight line over here, like a straight line. So the thermal flux is coming down, 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 but it looks over here at the boundary and some of them start coming back. So notice that there was a negative, sorry, there was a positive, uh, there was a negative gradient, which means a positive direction of current. So the current is that way. But when you have a positive direction of gradient, then you have a negative current. So you've got some neutrons being reflected, you see? So this is called reflection. And that's why this is called a reflector. So the hump in the thermal flux shows you there's a little mountain over here, there's a little peak over here. This little peak makes this little gradient become positive, which means that they're coming back to the core. So that's very good. So it's better utilization of neutrons. So that is why we call this a reflector. It's a mirror. So, so in words, what I'll tell you is that I can make a dilute homogeneous U235 water mixture, 22 centimeters of sphere, and surrounded by another 18 centimeters of shell of water without any U235 and call it my reflector. And this is a nuclear reactor. And it's going to start producing neutrons and it's going to start producing power. So ideally, in principle, you should be able to take a light bulb, to take your two wires, connect them. If you have converted the thermal energy into electrical energy, then you've started producing a voltage. You've started producing a voltage, so you can see a 60-watt bulb light up. And that's precisely what Enrico Fermi was planning in the University of Chicago in the, I think it was 1942. You can check the exact date when they made the world's first nuclear reactor and made it go critical. And so you can start a light bulb on it. Okay, now, if you're not satisfied with two-group results, then there's something called multigroup. Make them bigger and bigger. So the two-group was for one fast group and one thermal group. But I'm going to show you when you come to bigger discrete, bigger deterministic codes, then you have discrete groups as many as 262, and I'm going to hopefully spend quite a number of weeks, the later part of this course, on Monte Carlo simulations. Monte Carlo is the most fascinating um, thing that I found in my 3 degrees that I took in nuclear engineering, and I did my PhD in that, and I would just use it for anything that you want to do, because I think it's the best in the world. The best thing that we've got now. It's just like doing an experiment. So, so I think I did this thing with Monte Carlo also, but maybe later on. So 6 group diffusion cross sections, just to show you that you don't have to have two. There's 6 group data over here. So there are group transfer cross sections, and look at the structure of the 6 groups, because this is of interest to fast reactors. So they're not really interested in the thermal uh, energies, they're interested in the higher energies. So they break the higher energies into 6 groups. So, and there are very few fast reactors in the world. Okay, so then I'm going to show you a MATLAB program in the next lecture on how to solve the multigroup neutron diffusion equations. So there what you do is you discretize the diffusion equations for a group. So if you have, so I've called the group, I've given it the index I, and we've discretized it for R. So this is from Sekimoto, 2007. He converts them into difference equations. Difference meaning that phi I is related to phi I plus 1 and I minus 1. So what they do is, like, look at this for a sphere. You break a sphere which is physically going from R equal to 0 to R equals to some big R. You break it into a finite number of shells. So at the kth point, nodal point over here, you can write down the balance equation for current over here, and that comes out into a discretized form like this. So at the kth flux of group I, you see, this is the kth flux. So the flux at Rk, given by the superscript k, for the energy group I, so phi Ik is the flux at energy group I at the point Rk is related to the flux in the same energy group I at the point k plus 1. And so this is for the discretized form over here. Now, here I have not put the fission term, okay? Because to teach students, what I found is that start from a simple thing. Now, if fission were here, then where would it be? Then you would see a coupling. And you would see that in this expression over here, you would see a phi I minus 1 also, because the fast flux would be coupled with the slow flux. And if you had so many groups of neutrons, then there would be some coupling in between because of the fission spectrum, which means how many of the fission neutrons that are produced go into which of the groups that you're writing this equation for. Okay, but I don't want to complicate it at this stage. So at this stage, I'll just talk to you about a non-multiplying medium on which we apply the boundary condition. So on the left side, there's 1. So this, you can imagine, is the left boundary condition. And the right side, you'd have the right boundary conditions at the endpoint. Endpoint would be, for a sphere, R is small r at the number of mesh intervals plus a half, because the half comes out of centering the node at a point. So this I'll come to when we discuss the solution of this in detail. But what this gets to is that now this is the boundary condition on the right side, right? This is at the extrapolated boundary. So the 1 and 2 group, I think this is the most important thing that I want to say to you, is that the 1 and 2 group is extended into many group formulation through this general matrix equation, that C phi vector is B. So the vector phi is, uh, if you're doing 20 groups, and sorry, let's start by simple example. If you're doing 2 groups and you've got 20 mesh intervals, then 20 by 1 would be for the first group, 20 by 1 would be the second. So you'd get a uh, 40 by 40 matrix coming out of this. So you see the size, the complexity of the thing becomes huge. So look at the matrices. So the matrices become a tri-diagonal matrix. And that's the structure of this. So it becomes a tri-diagonal matrix over here, and you end up solving a huge equation. So this is the vector, it's the transpose of all of these. So the source for a non-multiplying medium, I'm going to show you an example where I put just a fast neutron source in the first interval, and I'm going to show you what it looks like. So I think I'll stop this lecture over here. The idea of this lecture in summary was to show you the 2 group equations for a core, the 2 group equations for a core and a reflector, and the multi-group diffusion equations for, uh, for any system, any nuclear system that you're considering. So the next lecture, I'm going to show you some numbers, and let's stop over here.